All right, now we're going to look at this idea of grounding a circuit. When we ground a circuit, it's basically telling us the location where the potential is zero. Instead of just picking a point and going around in a full loop to the other point and making the application of the loop rule that the sums are all going to be equal zero, it doesn't mean that the potential at that location is actually zero. So if we ground our circuit in this location, and this is the symbol for grounding, we know that at any point on this conductor that the potential is zero. So everywhere after that resistor up till that battery, everything here is zero potential. So we're going to graph the potential as we move through this circuit, just as we did before. At point A, we actually know it's zero, and then we're going to have our gain. Potential stays the same through the conductor. Potential drops across that resistor, stays the same value across the conductor, drops back down, and reaches our zero. So it doesn't really look any different than what we did in the last video. All right. If we change the location of the ground, something else has to happen. Now I can't erase that, so I'm just going to scribble that out. I'm going to move the ground up here. All right, so now everything at every point along here, it has a zero potential. If we move through our circuit graphing the potentials, what's going to happen is once we get to point B, which is going to be here. So this is where point B is in our circuit. It's in between those two resistors. So when the ground was here, it had some potential at this B point. Since we put the ground there, that has to end up at zero. So what happens here is basically the graph drops down so that at point B, the potential is zero. Now it's messing up my circuit over there, but no big deal. Now the changes in potential across that circuit don't change. So what this is going from zero to some EMF value here, all right, and whatever that change would be. So if I said that was a 9-volt EMF, the change from here to here is 9. Well, if I move it down here, the change from here to here is still 9, right? And then the drops are all the same voltage as well. So even if we apply the loop rule, we take the potential at point A, we end up with the same potential when we get back to point A, and the difference between those is still zero. It still follows the loop rule. So the ground can give us negative potentials at certain points. All right, we're here. All the potentials will be positive. Let's look at some more examples. So we're not going to do a full circuit. We're just going to take a section of a circuit. And say that the change in potential from A to B is going to be negative 8 volts. And the change in potential from B to C is negative 10 volts. So it really doesn't matter how much voltage we put at point A, as long as from A to B we lose 8, and from B to C we lose 10. So if we make the voltage at point A 20 volts, if we go to B, the potential should be 8 less, so we'll have 12 volts, then we'll lose another 10, and by the time we get here we have 2 volts. All right. If we put a ground in the circuit, all right, we can change where the voltage is 0. All right, so we now know that the voltage at B is 0 volts. However, the change in voltage isn't going to change across that resistor from B to C. If I have 0 volts at point B, the voltage at point Z has to be negative 10 volts. And the voltage at point A has to be 8 volts. So if the potential drop from A to B is 8 volts, 8 minus 8 is 0. 0 minus 10 is negative 10. Just changes the amount of voltage at the locations. It doesn't change the current through the circuit, and therefore it's not changing. It doesn't change the resistance, since they depend on their own properties. So let's look at another situation here. Put a full circuit. This will be 6 volts, 2 ohms, 1 ohm. And if we quickly were able to do Ohm's law, equivalent resistance is 3. 6 divided by 3 gives us 2 amps of current. So the change in potential across the resistors are going to be 4 volts and 2 volts. So as we move through the circuit, if I gain 6 volts here, so I have now plus 6 volts, and there's 6 volts all along that conducting wire. And then between this point and this point, I lose 4. So at this location, I have 2 volts. And then I lose my 2 volts. And then I'm back to my 0 volts. If now I ground the circuit here, I know that I have 0 volts at that location. And I can just move through the circuit. If I go down towards the battery, as I cross that resistor, I'm going to lose 2 volts. So at this location, I have minus 2 volts along that conductor. Then I'm going to gain 6. So 6 minus 2, I get 4 volts. So now I have the 4 volts along that conductor. And then as I cross this last resistor again, I'll lose that 4 volts and end up at 0. Didn't change the current, didn't change the voltage drop, just changes the value of the potential at the locations in the circuit.